Now we're going to look at a class of reactions called pericyclic reactions. These reactions are briefly described in 17.6. We are going to focus on cycloadditions. And particularly we're going to look at what's called the Diels Alder reaction. So this brings us to section 17.7. Now the Diels Alder reaction was discovered by Otto Diels and Kurt Alder. And in this reaction we have a conjugated diene plus a dienophile, and we are going to make a cyclohexene product. This is called a 4+2 cycloaddition. The reason why it gets this name is we have 4 carbons here in the diene and 2 carbons in the dienophile. And there are 2 different pi systems. We have the pi system of the diene and the pi system of the dienophile. Now we've already defined what a diene is. Let's define a dienophile. Okay, so a dienophile loves dienes. It is diene seeking. Alright, so let's look at the mechanism of this reaction. We have our diene and our dienophile. We are going to add heat, and then what happens is we get our cyclohexene. Now in this reaction it is a concerted process where the electrons from the dienophile, we're going to break the C6 C5 pi bond. We're going to break the C1 C2 pi bond, and then we are going to break the C3 C4 pi bond. When we do this, we form a sigma bond between C1 and C6 and C5 and C4, and a pi bond between C2 and C3. Okay. So if we look in our product, these are the sigma bonds that we form, and this is the pi bond that we form. Okay. There are no leaving groups. And when I say the reaction is concerted, okay, we have all bond formation and bond breaking occurring at the same time. If we look at the thermodynamics of this reaction, if you remember, in order to see if a reaction is spontaneous, we look at delta G, and delta G equals delta H plus negative T delta S. This is enthalpy. Delta S is entropy. In order for a reaction to be spontaneous, in favor of the products. Delta G must be negative. If we look at the reaction again, we broke 3 pi bonds. We form 2 sigma bonds and 1 pi bond. We went from 2 molecules to 1 molecule. Okay. If we look at entropy first, we can see that we have a decrease in entropy because we are going from 2 molecules to 1 molecules. So the randomness is decreasing. This term, therefore, will be positive. In order to have the reaction be negative, we have to look at the enthalpy. Now, sigma bonds are more stable than pi bonds. Okay, so that is what allows this reaction to occur. And so if delta H is sufficiently negative, we'll have a spontaneous reaction. The book goes on to say that we do need to watch our temperature. If the temperature is too high, then entropy will dominate. And delta G will be positive. Okay. So there's a balance as to how much heat we need to add to get the reaction to go forward. Now what we're going to do is we're going to break down this reaction into different parts to evaluate how the reaction works and how we can speed the reaction up and also improve the yield of products. Now, I am sticking within your chapter, however, I am going to jump around a little bit as far as the discussion goes. But all of this information is within Chapter 17, particularly Section 17.7. The first thing we're going to look at is the Diene conformation. Alright, when we have conjugated dienes, they have 2 low energy planar conformations. We can either have the S-trans conformation or the S-cis conformation. Now, only the S-cis conformation can undergo the Diels Alder reaction. And I'll explain why using orbitals. We're going to use molecular orbitals to look at why only the S-cis reacts by Diels Alder. Now, if you remember in class, we talked about the highest occupied molecular orbital, or the HOMO. And we also looked at the lowest unoccupied molecular orbital, which is called the LUMO. When we have a chemical reaction, we are looking at electrons. and often electrons are donated in making new bonds. Okay. Here we're going to use the molecular orbital theory to demonstrate molecular orbital overlap to make a new bond. And so the HOMO is going to give electrons to the LUMO. The reaction is going to be between the HOMO of 1,3-butadiene and the LUMO of ethylene. When we are in the S-cis conformation, we have orbital overlap between the HOMO of 1,3-butadiene and the LUMO of ethylene as shown here in this figure. You can see you have an in-phase interaction here and an in-phase interaction here. This results in sigma bond formation and your cyclohexene product. In the S-trans conformation of 1,3-butadiene, if we look at the HOMO, okay, so this would be the HOMO, the highest occupied of the S-trans conformation. Okay, and here is the LUMO, the lowest unoccupied of ethylene. You can see you only have orbital overlap for one carbon. That is why the S-cis will react and there is no reaction for the S-trans conformation. If we have a flexible diene, then you can have rotation around C2 and C3, and Diels Alder will occur. If the diene is not flexible, then there will be no reaction. So let's look at a case where it is not flexible and in the S-trans conformation. So here I have an S-trans diene. And I add my dienophile, and there is no reaction. However, if I have the S-cis conformation, and I add my dienophile, I can have product formation. And if I just number everything for you, so you see 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's our Diels Alder product. Okay, so remember we have to have the S-cis conformation for the Diels Alder reaction to occur. We can have an intramolecular Diels Alder reaction Okay, these reactions occur when we can form a 5-membered or a 6-membered ring. And the idea here is that there's flexibility in the molecule, so we can have rotation into the S-cis conformation. And I'll show you an example. One, two, 3, 4, 5, 6, 7, 8, 9. So if we look in this molecule here, we have both a diene and a dienophile. This molecule can rearrange in the following way because it is flexible. And we can have an intramolecular Diels Alder reaction. Here's the cyclohexene that results from the Diels Alder, and then we form a 5-membered ring on top. And I will number just so you can see where all the carbons belong. Here's our product. For an intramolecular reaction to occur, we have to have flexibility. Here, there's not enough room for this to rotate to reach the dienophile, so there will be no reaction. Okay, so in order to have the intramolecular, we need to have flexibility.